Okay, a dot diagram is just a different model of the atom, and the dot diagram shows only the valence electrons for the element. To draw dot diagrams, one approach is to look at the Bohr models, work out all the electrons, and then figure out how many are in the outermost energy level. We're going to do that with chlorine and carbon. So chlorine, you'd have to look on your periodic table and find out that chlorine has 17 electrons. You would know this because it has an atomic number of 17, which means it has 17 protons and 17 electrons. So we'd need to put 17, and I really have trouble doing these so that I don't, maybe I don't have the pen on. Okay. Get it back where it belongs. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the first 10. And then there's 7 more to go in the next energy level. One. Really bad about touching this and moving these around. Alright, so that's a total of 17 electrons, and you can see that 7 of them are in the outermost energy level, and so those are the valence electrons. So the dot diagram will have just the chemical symbol, which is Cl, and then it'll have 7 electrons because there are 7 valence electrons. Now, the electrons need to be in 8 basic positions. So if this were an element, if X were a chemical symbol, the electrons could go in these 8 places. And we won't have dot diagrams with more than 8 valence electrons. There are 1 or 2 exceptions to that. We won't be working with those. You probably wouldn't work with them in chemistry either. But anyway, so 8 possible places. And so notice I've got 2 at the bottom, 2 on either side, and 1 at the top. It doesn't matter where you start or where you end up, as long as your electrons are in those 8 places. Okay, so that's chlorine. Carbon has an atomic number of 6, which means it has 6 protons and therefore 6 electrons. So, I don't want the highlight. 1, 2, 3, 4, 5, 6. And we see that there are 4 electrons in the outermost level, so 4 valence electrons. So we would put carbon's electrons around carbon. Again, it doesn't matter. 2 on either side, 1 at the top, 1 on the side, 1 at the bottom, 1 on the other side. Any of those are fine. Sometimes you'll find as you're drawing molecules, when we get to that you'll shift them around in order to make things fit. So that's the basic rules for dot diagrams. If we get back to periodic table 2, you can see that there are Bohr models for the atoms. And notice in terms of the valence electrons, hydrogen has 1 valence electron. If you look at lithium, it also has 1 valence electron. Look down at sodium, it has 1. And in fact, this pattern follows all the way down the periodic table. So all of the elements in the first column have 1 valence electron. If we get back to here and go. Looks like I started this. Yeah, well, that's fine. I started doing this earlier and had a problem with my with the tape. Alright, so these have 1, and then as I said, that this pattern continues on down the periodic table. So they all have 1 valence electron. Next column, same deal. If we go back and look at the Bohr models, 2 valence electrons, 2 valence electrons. Again, it will continue on down. 3 for boron and aluminum, 4 for carbon and silicon, 5 for nitrogen and phosphorus, 6 for oxygen and sulfur, 7 for fluorine and chlorine, 8 for neon and argon. Notice that helium only has 2. That's an irregularity in the pattern that you just have to learn. You just have to remember that helium has 2. The noble gases are, we'll see their characteristics, but they tend to not react with anything, and that's because their outermost energy level is considered full. Once they have 8 electrons in the outermost energy level, they tend not to bond with anything else, regardless of whether that energy level is capable of holding more electrons. It won't as the outermost energy level. We'll talk about that a little bit more as we go. But helium only has 2 protons total. Its atomic number is 2, and therefore 2 electrons. But those electrons are in the first energy level, which, remember, only holds 2. So its outermost energy level is also full. That's why helium behaves like the other noble gases. So back to here, and so these will all have 2. And it doesn't matter where I put them. I put these at the top. I put one on either side here. Makes no difference. I do have a tendency to always start on the right side. There's no reason for that. It's kind of just habit for me. So my tendency is always to do that. Carbon, we said, has 4, and silicon did too. Germanium will be the same. Tin and lead. In fact, tin and lead often behave badly. They several of the transition elements and the little elements down here underneath, you'll see this group is called the metalloids, behave differently at different times. There'll be exceptions, but when I want you to be aware of them not acting as if they have 4 valence electrons, I'll give you that information. So don't worry about it. Our assumption, unless we're told otherwise, is that they have 4 valence electrons. This group will have 5. And I really encourage you to draw all these, just and think about what you're doing. Think about how many electrons these have. I think that it can help you to remember the information if you do that. Okay, and then this group has 7. And if we went back and looked at the Bohr models, we would see that that was true. Okay, and then helium, remember, only has 2, and the others here in this column have 8. So we don't have to go back and work out the Bohr models now to figure out the number of valence electrons. We can just look to see what column the element is in. I wouldn't ask you for a transition element to tell me what how many valence electrons there are, or to draw the dot diagram. They fill in an irregular pattern, and we're not going to go into that. That's why we don't even go to potassium and calcium when we're doing Bohr models, because they begin to fill in an irregular order. Phew. Alright, so you should be able to draw a dot diagram then for any of these elements. And just looking at the first column, they all have 1 valence electron. The next column has 2, 3, 4, 5, 6, 7. Helium has 2, and then the rest of these have 8. If you look at the next slide, I have those numbers labeled. Number of valence electrons, notice that's in gold, and it says all atoms in each column have the same number of valence electrons. And I've put the number at the top of the column. I put 2 and 8 because of helium. Helium has 2, and the rest have 8. Energy levels. In addition to being able to tell the number of valence electrons, we can actually tell the number of energy levels. And if we go back to periodic table 2, to these diagrams, to the Bohr models, you can see that all the electrons for hydrogen and helium are in the first energy level. When you go to the next row, all the electrons are able to fit in just the first two, so in 2 energy levels, all in 2, and then the next they all fit into 3 energy levels. And again, that's a pattern that holds through the rest of the periodic table. So that hydrogen and helium have only 1 energy level. The energy levels are different regions in the electron cloud, and we represent them on a Bohr model just as a ring. Of course, they really are 3-dimensional. They're like balls, and actually some of them are in different shapes. But we can't draw that very easily, so we just draw them as rings. So those 2 elements will have only 1 ring, 1 energy level. These will have 2. The next row will have 3. The next row will have 4. And that even includes the transition metals. So I could ask you about a transition metal, like I think iron's in that first row. How many valence, no, not valence electrons. How many energy levels does it have? And you would just look to see what row it's in, and you'd put a 4. The periodic tables that we use, the ones that I gave you on paper, do have these numbers listed. So that makes it much easier in terms of figuring that out. Every periodic table may not have that, but it's very easy to count down, right? Okay, these all have 5, 6, and then 7. All right, that's it.